talk, please type those into the Q&A box. And at the end of the presentation, I will read them out and the presenters will answer them. So the first presentation today is from Sarah Dean from UC Berkeley. So Sarah, if you're ready to share your screen, the stage is yours.
Yes, I am. Thank you very much. All right, click share. Great. Yeah. So hi, everybody. I'm happy to be presenting here today, especially after such an apt tutorial by Professor Andreas Krauss, talking about sort of safety and reinforcement learning and in machine learning. So today I'm talking about this paper called Guaranteeing Safety of Learned Perception Modules via Measurement Robust Control Barrier Functions. And this is joint work with my collaborators, Andrew Taylor, Ryan Cosner, Ben Recht, and Aaron Ames at UC Berkeley and at Caltech. So this work is really motivated by the fact that, in our increasingly digital world with a variety of digital technologies, robotic systems have the ability now to use increasingly complex sensors, whether it's cheap cameras, because camera sensors are cheap, or more advanced sort of imaging sensors and depth sensors. So vision in particular kind of motivates this work. And it's a complex sensing modality that is not as straightforward as our traditional sensors. But at the same time, it's very valuable and can provide a lot of rich information about the scene and about the state of a system. So because these sensors are more complex, they require more complex calibration routines. So this is sort of maybe a familiar picture of like a ROS camera calibration routine. But in general, doing this kind of calibration might require something data-driven or use some kind of learned model. And this leads to opportunities for measurement model error. And that can have sort of dire consequences if we want to take our systems out of the lab and put them into the world. So this picture here is from a National Traffic Safety Board report on a crash of a Tesla driving on autopilot on the 101. So sort of local to me. And basically what happened in the crash is that the car failed to sort of detect that it was in this space between to the exit and the highway and remained sort of in this dead space until it hit the barrier. And so it's sort of important that, yes, cameras provide a lot of great information, but how can we make sure that they're safe and effective for controlling a system? So in this work, I'm not going to try to solve all of self-driving cars. That might be a little too much, but I will consider the setting of nonlinear control affine dynamics. And I'll suppose that these functions f of x and g of x are known ahead of time because the system is sort of well specified. It's a robot that we built. Now, to consider safety, I'll define this set C as this zero superlevel set of some function h. And this is just some subset of the state space. And I'll suppose that what we mean by safety in this setting is the invariance of the set C. So the system must remain in this set for safety to be guaranteed. And this is not a probabilistic notion of safety. This is sort of very deterministic. What makes the system different, what makes our setting different from a more traditional sort of nonlinear control setting is that the system is observed by some complex function, P of x, which gives rise to observations y. So for example, we might have a robot, which rolls around it and has different angles and different speeds, which is observed through a camera, which gives rise to some observation, which may be some image. And then to sort of understand the state of the system, we will back out some estimated state x hat from a function q. Q hat, which I'll refer to as either an approximate inverse, so it's approximately trying to invert this mapping P. I'll also call it a perception map because it's sort of perceiving the system state from an image. So before we get more into this observation model, let's go through safety. So how does one maybe guarantee safety, or what are some ways to do it in these nonlinear systems? We actually just had a great review of that. I'm going to focus on this method using control barrier functions. So remember this function h, which defines our safe set. It will be called a control barrier function if there's some extended class K function alpha such that the following inequality holds. So looking at this inequality, it says that this sort of inner product between the derivative of h with respect to the state and sort of the system dynamics is bounded below basically by some negative value. And if we want to sort of draw a picture, it looks a little bit like this. So we sort of have the way the system evolves, the direction of system evolution is pointing inwards at the boundary of the set. That's a nice way to think about it. Basically what we're doing with this condition, what we're asking H to be, is to ensure the existence of some control action U such that, right, this state evolution multiplied by the derivative is bounded below. In other words, that the derivative of H itself with respect to time is bounded below. And really what this means is that by choosing a U such that this property is satisfied, we're ensuring that H remains positive. And recall by definition of our safe set, this shows that the safe set is invariant under that trajectory. So that's why this is a great way to ensure safety. And this is the framework that we're going to use. So sort of this specifies how we want to think about choosing control actions. It allows us to define a set of inputs for each state, which will help the system to ensure safety. And we can actually use this as a safety filter for any given controller, either hand designed or, maybe a learning controller, can be filtered using a convex optimization problem because this condition on our control input U is actually this linear constraint. And I also want to point out on this slide, I'm going to start using this Lie derivative notation. So LF, the Lie derivative of H here is just this product. And that's just for simplicity. Yes. So that was great, and this is sort of a known way to keep systems safe, but it relies on knowing exactly how the system will evolve. If you don't observe the system state directly, that's something that you can no longer predict perfectly. So our setting has this imperfect state observation, which is a problem. There's actually some related work that considers slight variations on this, where the state is also imperfectly observed due to things like noise. And it's not exactly what we'll be doing here, but they give rise to sort of similar conditions. So since we don't know what the state is, we're left with sort of reasoning about possible states given what we've observed. And so given an observation Y and sort of doing this perception map that might be imperfect to have an X hat, and then supposing there's some errors there, we get this set of states in state space, which sort of this calligraphic X of Y. And now instead of trying to ensure this control barrier condition for the single X, we have to try to do it for all X's because we don't really know where we could be. So what do I mean? Like, what does the set actually look like? So recall X hat here is given by this Q hat of our observation. And so if there is some true inverse, you can sort of rewrite the equation this way and see that really we're just observing the state plus some error. So this is our perception error, E of Y. And that's what I'll talk about, because this sort of defines, a set might be centered on this X hat and its radius is determined by this E of Y. And so supposing that perception error is bounded, we can now sort of rewrite this barrier condition, this robust barrier condition, as follows, where we're now sort of minimizing the left-hand side over all possible errors. This is not really an easy expression to work with because those Lie derivatives are certainly going to be nonlinear. Remember that we were trying to use this condition as a constraint and optimization problem, so it sort of ended up get this like max-min kind of condition, so it's not great to work with. So we'll do sort of a robustification. And that motivates our definition of measurement robust control barrier functions. And so we define a set of inputs which ensure robust safety as follows. So looking at this condition inside the set, the difference from the sort of traditional control barrier function condition is this additional negative term on the left-hand side. And this is for some given functions A of Y and B of Y, so functions of our observation, which will be positive. And we have this multiplication by the norm of the control input. This term captures the uncertainty in our system that arises because of our imperfect observations. And so combining this with some of the intuition from the previous slide, we have this result that as long as we can bound the system's perception errors by some epsilon of y, so a scalar value epsilon, and the Lie derivatives and the barrier function are Lipschitz, then by setting A of y and B of y as follows, sort of depending on the continuity and on those perception errors, any controller inside this robust safe set will render the system safe. So we have now a way to constrain the system, or to constrain our control inputs that will guarantee robust safety. And now we can use this in an optimization problem to use a similar sort of safety filter. So comparing this to our previous control barrier function problem, we're now sort of doing the same, trying to stay close to a given desired controller with a constraint now which has that extra term. And inspecting this, this is a second order cone program because of that norm of U that shows up in the constraints. But it's still a convex problem and therefore can be solved efficiently. One question to ask though is this actually feasible? So the feasibility of the normal control barrier function optimization problem is guaranteed by the definition of control barrier functions. And here, it's not necessarily going to hold anymore, but we can ensure its feasibility if the errors are small enough. And in the paper, we go into a little bit more detail on this, but making those errors small under different measurement models can be done from data. So essentially by sort of densely sampling within that safe set, you can guarantee that your errors are small enough to ensure feasibility. I'll also point out that the errors don't have to be that small because this problem can still handle some sort of non-negative errors, which means that your system can remain safe even with imperfect observation. So I'll just wrap up by sort of motivating that this can work at least in a simulated system and show how useful it can be to add this robustness. So the system I consider is a Segway robot constrained to planar motion, which means it moves only forward and back, and that safety will be defined by its pitch angle. So we just don't want this robot to fall over. Specifically, it's defined sort of by this set in pitch angle and pitch angle rate space. And to sort of match our perception setting, we'll say that the pitch angle and the position are not accessible by anything but some camera image. So there's many ways you could try to sort of back out the position from the image. We're just going to go full on machine learning and just do it from data. So training data, 800 training images were collected from a grid of different angles and different positions. These are some examples. And a model mapping the image to the position and angle was trained with sort of this non-parametric ridge regression with radial basis functions. And on a held out set, it actually performs fairly well with sort of errors around 0.1 or 0.2 radians, at least in angle. And so I'm running out of time, but I'll just show that without in closed loop, with just a standard safety filter, the system actually does not remain safe and leaves the safe set. Although it does ultimately come back, the safe set is not invariant. And so we failed to satisfy the right property. However, with the robust condition, we are able to stay in this set regardless of the perception errors that we have. And that's what this demonstrates. So in conclusion, we propose measurement robust control barrier functions, which can ensure safety. They're a convex optimization problem, and it depends on system continuity and bounded perception errors. Thank you.
Thanks very much, Sarah. So yeah, if the audience has any questions, please type them into the Q&A box. We might have time for one question, I think. And maybe as we're waiting, I'll ask a question of my own. So if I understood the architecture correctly, it looks like the perception module is trying to reconstruct the full state of the system. And I wonder for a lot of problems that may be unnecessary. So the state might contain information that's not task relevant. So I wonder how your architecture deals with that.
Yeah, so I think really as long as you can guarantee safety, as long as whatever your safety condition is, like only depends on that subset of the state, then I think it would sort of fit directly into this framework, where you might have sort of like a lower level controller that deals with like accelerations and torques, and then your high level controller is just on position. I think that's like a good example of where this fits in directly. On the other hand, if you really do need to reason about sort of like velocities, and you can't measure that from your camera sensor, then that's a reason to extend this into sort of a state estimation setting.
Thank you. All right, it doesn't look like we have any questions so far. Yeah, maybe I'll just remind everyone, I guess if you don't get a chance to ask a question here, the authors will be available at the parallel interactive sessions later today. So you can ask your questions then. All right, so our next speaker is Marcus Pereira from Georgia Tech. So Marcus, whenever you're ready, the stage is yours.
Thanks, Ani. I just wanted to verify, can you see my slide? It's just an empty slide. Sorry, a slide with the title of my presentation.
Yes, but I think you might be in presenter mode. We see your notes as well.
Oh, I see. Okay. Sorry.
It's still in presenter mode.
Maybe I should try to share screen again. Oh, sorry. How about now?
Yes, looks good.
Thank you so much. Thanks for the patience. Okay, so good morning, everyone. My name is Marcus Pereira, and I'll be presenting our work on safe stochastic optimal control using barrier functions and deep forward-backward SDs on behalf of my team at the Georgia Institute of Technology. In this work, we propose a novel algorithm for safe reinforcement learning, an architecture to solve constrained Hamilton-Jacobi-Bellman equations that ensures safety not only during testing, but also during training. That is end-to-end differentiable, and that combines the principles of safety and optimality into one framework under uncertainty. We achieve this by bringing together stochastic control barrier functions, deep forward-backward SDEs, and the OpNet differentiable convex optimization layer to produce an end-to-end differentiable, safe stochastic optimal controller. Thus, our work lies at the intersection of three very important fields in robotics research, namely safety, stochastic optimal control, and end-to-end deep learning architectures. We guarantee safety through SCBFs, optimality through deep FPSDs, and end-to-end differentiability through the OpNet layer, thus giving our framework. Before we take a closer look at each of these building blocks, let us quickly look at the problem statement. We assume that we are given control-affine nonlinear system dynamics, where X, U, and W are system state, controls, and Brownian noise vector respectively, and F, G, and sigma are the uncontrolled dynamics, actuation, and covariance matrices. We are also given a cost function that defines the task to be completed within a fixed time horizon. This cost function is comprised of a running state cost, a quadratic running control cost, and a terminal known cost function phi. We are also given a barrier function that is task specific and hand designed, and a safe set that is a super level set of this barrier function. Also, the boundary of this set is where the barrier function is identically 0. Finally, we also assume that we start inside the safe set. Now, we can define the value function as the minimum cost incurred starting from state X and time t. Notice that this is a constrained minimization problem, as the only admissible controls are those that ensure that the state is inside the safe set for the entire time horizon. Then, using Bellman's principle of optimality, one can easily derive the HJB PDE by simple application of Ito's formula. Because of a given terminal condition, the HJB is a backward PDE, and it suffers from the well-known curse of dimensionality. Now, this can be tackled with well-known non-sampling-based methods such as STDP Galergan approximation, or sampling-based methods such as the path integral control framework or FPSDs. We focus on FPSDs as it is the most general of these frameworks. We start with the first building block, stochastic CVFs. These extend deterministic CVFs to stochastic dynamical systems. We define a zeroing stochastic CVF as any function h that defines a CF set and guarantees safety if for some class K function alpha, the following inequality holds for all time. We refer to this as the safety constraint. Now notice that the left-hand side of this constraint is the Ito time derivative of the barrier function in contrast to the regular time derivative in the deterministic case. Using the above definition, we can now state the following theorem. Assuming that there exists a control u of t prime such that for all t prime less than t, the above inequality is satisfied, then the process x of t has remained inside the safe set with probability 1. The proof of this theorem is available in the appendix of our paper. Next, we look at deep FPSDs, which are deep learning architectures that solve general parabolic partial differential equations. This is achieved by application of the so-called nonlinear Feynman-Cach theorem that links the unique solution of PDEs to systems of FPSDs. The AJB PDE that we just looked at, that is in fact a parabolic PDE. Now, applying the nonlinear Feynman-Cach theorem to the AJB PDE yields the following system of FPSDs, wherein the forward SDE is the system's dynamics, and the backward SDE is the value function process. Why do we care about deep FPSDs? That is because they simplify solving systems of FPSDs. The main technical difficulty in solving FPSDs is that the backward SDE is technically difficult to solve. This is because solution of the backward SDE requires backpropagating conditional expectations in order to get adapted solutions. And this method traditionally has been known to be prone to regression errors and therefore cannot scale. Now, deep FPSDs, on the other hand, they allow forward propagation of the backward SDE by casting it into a simple deep learning problem, as we shall soon see. Finally, we look at the third building block, which is the OpNet differentiable convex optimization layer, which generalizes a neural network layer as a solution to a quadratic program. In the forward pass, an interior point solver outputs the solution to the QP. The inputs to this layer could come from regular neural network layers or from other OpNet layers. Now, in the backward pass, one simply differentiates through the KKT conditions evaluated at the solution of the forward pass. This is very efficient. It does not require automatic differentiation through the unrolled graph of the QP solver, which would then make application infeasible for high dimensional problems. Now, these gradients can be computed with respect to any of the layer parameters. Finally, why do we care about the OpNet layer? That is because deep FPSDs require differentiability of all its subcomponents, and the OpNet allows embedding argmin QPs into the deep FPSD framework. Putting all of these components together, we have the forward SDE systems dynamics, the backward SDE value function process. These are handled by deep FPSDs. We have a QP at each time step to solve for the optimal control and safe control. This is handled by the OpNet layer. And finally, the safety stochastic CVF constraint inside the OpNet layer. We now look at our proposed deep learning architecture. We are given an initial state, and we know a terminal cost function that allows us to compute the value function and its gradient at the terminal time step. However, we want to avoid backpropagating the backward SDE, but the initial value is unknown. So therefore, we just make this initial value as a trainable network parameter. And in fact, the known terminal value and its gradient now become prediction targets for this deep network. Remember how I said that we can now forward propagate backward SDEs? This is how we do it. We then initialize the weights of the network. We use the network to predict the gradient of the value function at the initial time step. This in turn is used to forward propagate the value function with sample noise. This gradient is also fed back into the OpNet safety layer to compute a safe control. The safe control is used to forward propagate the system's dynamics with noise. Now the new state is fed back into the LSTM and is used to predict the gradient of the value function at the next time step. We now repeat this process of forward propagating the value, computing a safe control, and forward propagating the system state. And we continue this process until the end of the time horizon. Finally, using the known targets and the predicted value and its gradient, we compute a loss function. And then using any stochastic gradient descent variant, we can train the weights of this network. For all our simulations, we used the following stencil to construct barrier functions. The position constraint of the stencil, it defines the task and is task dependent, and it defines the original safe set. For example, suppose we want to avoid an obstacle, then this position constraint would literally mean the distance from that obstacle. It would be strictly positive away from that obstacle and 0 at the obstacle boundary. However, notice the squared velocity term. Because of the addition of the squared velocity term, we have the following implications. The first is we create additional boundaries, and it modifies the original safe set. Adding this term would mean avoid certain positions at certain velocities instead of just avoid certain positions. Also notice that because at the boundary, the position constraint becomes 0, the only allowable safe velocity at the boundary is 0. And that means the system has to slow down as it approaches the boundary. The other implication is that the relative degree of this system, of this barrier function, is 1. As a result, the Lie derivative of h is not 0, meaning we can use control to satisfy and enforce the safety constraint. Let us consider a simple scalar example for intuition. Suppose that the safe interval is -1 to 1, and our position constraint would look like so. Then, as I increase mu from 10 to 1 to 0.1 to 0.01, notice the size of this ellipse keeps growing. That means the allowable safe velocity at the center of the interval keeps growing. Thus, one can tune mu to allow more aggressive behavior inside the safe set. Now we present some highlights from our simulations. We start with the cart pole balancing task with a time horizon of 1.5 seconds. The initial position is the vertically upward unstable equilibrium position, and the goal is to stabilize around this unstable equilibrium position. For comparisons, we use unsafe deep FPSDs, and then we progressively increase the difficulty of the problem by first imposing only pole angle constraints and then both pole and cart position constraints. In the video alongside, the gray boxes are cart position bounds, and the red area represents unsafe pole angles. As seen in the video, initially the unsafe controller completely violates both bounds because it is simply blind to both bounds. Then next, we impose only pole angle constraints. Now notice the cart can save the pole from falling by moving very fast in one direction, but however, this violates the cart position bounds. Finally, we impose all constraints, and now the cart is able to stay within the bounds and save the pole from falling as well for the entire time horizon of 1.5 seconds. At the end of the day, they all learn the same policy, and therefore, we reiterate the need to stay safe during the entire learning process. For our next example, it consists of 4 2D cars, each with a nonlinear kinematic model, starting at 4 corners of a square grid as seen. And the task is to swap positions with the diagonally opposite car while avoiding collisions. For this task, we used 4 choose 2, that is 6 barrier functions for each car pair, and the barrier functions were based on the same stencil that we saw earlier. As seen in the video, initially the cars moved towards the center and they stopped short of their targets. However, these states get associated with a high cost or high value and therefore are non-optimal. Therefore, as seen, the cars try going around the targets to avoid these non-optimal states. As iterations progress, the controller tries to strike a balance between optimality and safety. Finally, they all learn to move towards the center, orbit around the center, and then gracefully move towards their targets. In conclusion, we introduced a general framework for safe learning control grounded in first principles by leveraging connections between FPSDs and nonlinear PDEs. We employ stochastic barrier functions to guarantee application of safe control at each time step, and utilize OpNet's efficient gradient computation to make this entire framework end-to-end differentiable. Due to the general applicability of the nonlinear Feynman-Gach theorem, one can consider many theorems, many algorithms emanating from this work. To name a few, mean field games, L1 stochastic control, and others. Finally, this work is also a stepping stone for more complex safety critical applications, such as aerial and robotic and space vehicle navigation. We would like to thank NASA and NSF for sponsoring this research. Thank you for listening, and I would love to take any questions if you have any.
Thanks very much, Marcus. Yeah, any questions from the audience, please type them into the Q&A box and I will read them out to Marcus. All right, we have a question. So the question is the approach going to be open sourced? So the software and the code for the approach, is it going to be available on GitHub or an open source platform?
Thanks for asking that question. Yes, we are definitely working on making a public repository for that, and we will try to also have instructions on replicating all of our experiments.
Thanks. All right. One more question. So thanks a lot for the great talk. This is from Stochastic. Could you comment on the scalability of this approach for vision-based tasks? So maybe scalability in terms of sample complexity and computation as well.
That's a very great, very important question. In terms of scalability for vision, we could consider different approaches, such as, we have also worked on belief space deep FPSDs that tries to incorporate observations and observation noise. But if you go and look at some of our published papers, we have shown the deep FPSD framework to scale up to 100 dimensions and above. For example, on portfolio optimization problem where the dimensionality comes from the large number of stocks processes. So we have definitely shown examples in the past, and we are working in that direction to now scale this to complex models in simulators.
All right, thank you, Marcus. Okay, so our next presenter is Rohan Chitnis from MIT. So Rohan, whenever you're ready, the stage is yours.
All right, can everyone see my screen and hear okay?
Yes, looks good.
Okay, great, so I'll get started. Hi everyone, my name is Rohan. I'm gonna be talking to you about our work on CAMPS, learning context-specific abstractions for efficient planning and factored MDPs. So it should hopefully be intuitive that for any decision-making agent, when it has a lot of options or like a lot of choices as to what it can do, this can result in taking a long time for it to actually make any decisions or plan out its actions. This is very, very common issue in robotics. So for example, consider this navigation among movable obstacles NAMO task shown here, where the goal is just for the robot in the bottom left to get to the location in the top right, marked in red. If you try to use a kind of general purpose planner for the setting, it can be very slow just because of the number of options that are available here. For example, which rooms should the agent go through to try to reach the goal? Which objects should it move out of the way? When should it move those objects? How should it control itself to be able to follow the path that it thinks of? We can also say very similar things happen in manipulation settings. So consider here a problem where the goal is to move these red objects from the table on the left into the empty bins on the right. We can make a very similar statement here, which is that if we were to try to use a general purpose planner, which doesn't leverage any specific heuristics about this problem or domain, then it can be very slow just because of the many options available to the agent in these continuous spaces. So basically, if we acknowledge that planning suffers when too many choices are available, what we're interested in this work is following a long line of related literature that addresses the question, can we basically find a way to narrow down the space of choices that our planners have to consider? And so you might be thinking an extreme solution would be, why do we have to do planning at all? We should learn a reactive policy, right? A mapping from states to actions, and then we can just kind of follow that policy once we've trained it. And that's great, right? We don't have to plan. This is definitely true, but it does have its downsides. Learning a reactive policy can be very expensive to learn in terms of data efficiency. It can cost a lot to acquire the necessary data. And furthermore, it's kind of unlikely for such a policy to generalize well in the kinds of settings we are interested in this work, which are long horizon, continuous robotic planning problems. Very hard to get a policy to actually perform well in such problem settings. So we can already say that what we're really interested in here is optimizing a trade-off, which hopefully you all find to be intuitive. So supposing we have a task omega marked in blue, what we really want at the end of the day, I hope everyone agrees with this, what we really want at the end of the day is that we want a policy that performs well at whatever that task is, but also it doesn't take the robot too long to actually come up with that policy. So if we think about this objective, what we really want is a kind of sweet spot between two extremes, right? So on one extreme, we have let's just plan for that task that we're given. It's likely to get good rewards because you're kind of intuitively considering all the different possible options. That's like what planning is, right? But on the other hand, it's going to cost a lot to actually come up with the policy that achieves that high reward. On the other extreme, we have policy learning. So say we already have trained a policy on some different tasks. Using that policy for this new task omega is unlikely to be very expensive, but if it fails to generalize well, then you'll see it suffer in terms of reward. So in trying to find a sweet spot for that objective, the first key idea of our work here is that we should make use of constraints, right? Constraints simplify planning because they basically guide the planner. And so the first key realization is that agents can actually impose constraints on themselves for the sole purpose of making planning more efficient. So these aren't physical or environment or safety imposed constraints. These are constraints that the agent chooses for itself. So let's look at an example. Going back to the Nemo example, we could say that maybe the robot might only consider paths that go through these rooms. And the reason that this would be help a planner is because now the planner doesn't have to consider paths that go outside of these rooms marked in yellow. We can say a very similar thing in the manipulation case. We can maybe the robot could constrain itself to only consider certain ways of grasping the red objects, like top grasps only, and only consider placing into certain bins. So this next key idea, which is actually the main novelty of our work, is that these constraints can actually help in an even greater way. Not only do they help guide the planner, but also they can make aspects of the problem irrelevant. So the key piece of formal machinery we use here is the notion of context-specific independence. This is due to Boutelier from 1996. This is a notion that can't actually be expressed with a classical Bayes net. And it basically is conditional independence of two variables, but conditioned on specific assignments of other variables. So a simple example would be, if I am in the context or the constraint that I am staying inside my house, then the outfit that I choose is going to be independent of whatever the weather might be outside. So we can make use of this going back to our example. So we've already seen that maybe the robot says, okay, I'm only going to stay in these rooms marked in yellow. But the context-specific independence lets us go a step further and then remove these other objects from the planning problem, therefore simplifying planning. We can also say a similar thing for the manipulation case. So here, if the robot chooses to only grasp these red objects from the top, then it doesn't run the risk of its gripper colliding with these blue objects here. And similarly, if it only places in these bins here, it doesn't run the risk of its gripper colliding with these green objects here. So we can say that these objects become irrelevant. So it's really important to realize that these blue and green objects are not like always irrelevant to this problem instance. They're only irrelevant because of the constraints, that the robot imposed on itself, that it's only going to top grasp and only going to place in certain bins. So now we're ready to kind of put everything I've talked about together. And so here's what a CAMP is, context-specific abstract MDP. So if you're given a factored MDP and a particular constraint on your states and actions, then a CAMP is like an abstracted version of that MDP. So the first thing it changes is that violating the constraint leads to an infinitely negatively rewarding absorbing sync state. So basically, please don't violate that constraint. And the second thing is that we can make use of the context-specific independences I mentioned to remove things that are irrelevant under that constraint. So hopefully from these two things, you should be able to see that planning in a CAMP is usually going to be a lot faster than planning in the original MDP. You have a simpler MDP to plan in. Of course, this does come at the cost of reward optimality, but as we mentioned before, we're interested in this trade-off objective where we don't necessarily need the highest reward policy, but we really care about the speed that the amount of computation basically that's required to obtain the policy that achieves that reward. So at this point, you might be wondering, okay, this is all great, but how do we actually do this stuff? So for example, how do we actually figure out what factors here are irrelevant under the constraint? And where does this constraint even come from? How do we know what constraint to decide on? So these are good questions. And to answer those, we kind of set it up as a learning problem. So very broadly, we're imagining we have a multitask setting where you have a bunch of training tasks that all have a shared transition model. And from these training tasks, you can learn these two things that I mentioned. So the first thing you can learn is what are the context-specific independences that hold in this transition model, so in this domain, basically. The way we do that is we approximate it with Monte Carlo estimation. And the second thing that we learn is a constraint selector, which is basically a neural network that's conditioned on the problem instance. So it takes in the initial state and information about the reward. And it's a multi-class classifier, and it predicts basically what constraint is the best one for the agent to impose on itself. So just to kind of summarize everything I've talked about here, remember that the objective we care about is this trade-off between reward and computational cost. So if we were to apply just a planner on our tasks, it's likely that the planner would be able to solve the tasks, but it might take a long time for the planner to come up with a policy that does so. Policy learning would be another approach. If you have your policy trained, it's very fast to do inference with that policy. But if it didn't generalize well, it's unlikely to perform well in terms of reward. So we see camps as a kind of sweet spot. So what we're going to do is we're going to have our problem instance. We're going to use our context selector that we've learned to pick a particular constraint or context that the agent should impose on itself. We use our learned context-specific independences to figure out what aspects of the problem became irrelevant. Now we have a camp that we can plan in. It's a simplified version of the full MDP. And then we can apply the policy that comes out of our planner on the original problem. So this is going to provide a good sweet spot in terms of the objective we care about. So experimentally, we tried camps in many different domains, from robotics to classical planning to grid worlds, with several different planners as well, from task and motion planners all the way to classical things like value iteration, graph search, that stuff. Across all these domains, we found that camps generally allow for fast and rewarding planning, so a good sweet spot like we've been talking about. So here what these graphs show is on the y-axis you have returns in the environment, and on the x-axis you have computational cost. So up and to the left is better. And so these blue dots, which are camp, basically you can see that across all of these problem settings that we consider, camps tend to perform very well. Another particular result that I wanted to highlight is that we were able to find that camps actually outperform Stillman's NAMO-specific planning algorithm without any NAMO-specific reasoning. So what's really cool is that camps are able to perform well on our trade-off objective without actually having specialized heuristics for each of these different problems. So it's a very general approach that you can apply to many different kinds of problem instances. Now just to show some videos of the behavior. So here is the navigation example we've been talking about. So here it's kind of planning, and now it's going to execute the policy. So you could see that while it was planning, it ignored all of these objects in these other rooms here. And now while it's executing its policy, you'd better hope that the policy that it's following here actually obeyed the constraints that that it was using while planning, right? Which is that it only stays in these in certain rooms here that were marked in yellow. We can also see a video for the manipulation setting. So again here, as we talked about before, the agent is only constraining itself to use top grasps on these red objects, which is why you see that it's only going to pick things up with a top grasp. This allowed it to simplify its planning problem by not having to consider the blue and the green objects. But what you see is that as a result of doing a top grasp, the agent realized that because it has to use a side grasp to place the objects in bins, it actually needs to do this little handoff procedure where it changes its grasp on the object before placing it into the bin. I also want to note here that, that this fact that these blue objects became irrelevant as a result of using only top grasps on the red objects, that's not something that we told our system, right? This was something that was learned on the training tasks by our learning approach. So yeah, hopefully you find that to be a cool result. And that's about it. So with that, our code is available on this GitHub URL. So feel free to check it out if you're interested. And we'll also be at interactive session number 3 today. And at this point, I'm happy to take any questions.
Thanks very much, Rohan, for the great talk. I think we have a couple of questions. So the first question is from Sushant Veer. So In general, how would you ensure that the imposed constraints do not violate the solvability of the task?
Yeah, great question. The answer is that, like, theoretically, you absolutely we can't. So nothing in our problem statement stops you from being able to impose a constraint that says, I'm never going to leave my house if the goal is to get to the grocery store. But remember that we are learning a model that is going to predict what would be a good constraint to use. And that model is trained to select constraints that optimize our trade-off objective that I keep talking about. So if you aren't getting any reward from using a particular constraint, the value of your objective will be very, very low because you should be having a policy that uses. Now, one thing to note is that if you crank up the term, so that policy is a trade-off, right? Sorry, that objective is a trade-off. If you crank up the term really high on the second term, which is just like how long does it take to compute, then you're actually always going to pick constraints that just say, I'm just going to stand here and do nothing ever, because that requires very little thinking. It's never going to get me any reward for any task, right? But so the weight that you put on the trade-off between these two terms and the objective does actually matter.
Thanks. And I think there's another question from the audience. So how do camps fare in non-stationary environments, such as the multi-agent navigation setting?
Yeah, so I think one issue that arises in non-stationary environments with respect to what we're doing here is one of the limitations of the current approach is that we only consider a single constraint or context to be imposed on the agent for the entire episode. Now, if there's non-stationarity, or to be honest, even if there isn't non-stationarity, but in certain situations, it can be useful to change your context or your constraint as the episode continues, right? So the constraint you impose at the start may not be the constraint you want to impose later on. So this kind of suggests a more interesting, an interesting direction for future work, which is to bring in the notion of sub-goals into this whole thing, right? So so to address the non-stationarity question, I would imagine that maybe a good way to handle that would be if you have kind of a sub-goal at any given time, and as there's non-stationarity in the environment, things may change. You may decide, okay, my current sub-goal is no longer worth pursuing, or maybe you've achieved it. Now I'm going to move to the next sub-goal, and I want to generate a new camp for that sub-goal. And that's something we don't do right now.
Awesome. Yeah, thank you, Rohan.
Thank you.
Yeah, so I think that concludes our session on planning and control. So yeah, thank you again to all the speakers, and thank you all for attending. So we now have a little bit of a break in the program. So the conference program will resume in about 7 minutes with the parallel interactive sessions. Thank you.